I'm an assistant professor in aerospace engineering, and I work on formal verification and programming languages. So it's my great honor today to introduce Alex Aiken, who's the Alcatel-Lucent Professor of Computer Science at Stanford University. So Alex grew up not too far from here. He actually grew up in Bowling Green, Ohio, and in a family of music faculty. And he initially wanted to do a career in music and studied music and computer science at Bowling Green State University. But after spending, about a year in Austria as a trombone player, he decided to become a PhD student at Cornell University, studying programming languages. After his PhD, he spent 5 years at IBM Research, then 10 years as a faculty at Berkeley, and then since 2003, I think, he's been a professor at Stanford in computer science. So his research interests are in programming languages, and he will talk to us today about the Legion system, which organizes parallel programming not just for computation, but also but also for organizing data. He's an ACM fellow, a recipient of the ACM SIG Plan's Programming Languages Achievement Award, and the Phi Beta Kappa's Teaching Award, and he's a former chair of the Computer Science Department at Stanford University. And finally, Alex and his family are very passionate about the outdoors and about traveling, and they've taken a lot of amazing trips all over the world. Thank you for being here, Alex.
Yeah, thank you very much. Thanks for the wonderful introduction. So this is working fine when we tested it earlier.
Well, and it's seeing it. That's very interesting.
There we go. All right, thank you very much. Yeah. All right, well, so it's a real pleasure to be here. I want to thank the organizers for inviting a trombone player to present at the symposium. I will not talk too much about trombone playing today. I was going to talk instead about a programming system that my colleagues and I have been working on. It started out as a very small project maybe 10 years ago and has grown steadily over time. And I'll just talk about a little piece of it today, but I hope it's something that will kind of give you a sense of what computer scientists do, and particularly the people who think about designing future programming systems do, as well as some of the challenges and opportunities that we have. So anyway, without further ado, as was mentioned already, we are entering the age of exascale computing, and Doug, when he's here later today, will, I'm sure, mention both Frontier and Aurora, the two exascale machines that the DOE is building. Actually, Frontier is very much in existence. I can say I've personally run programs on it. Aurora's coming along. The test beds are there. So these are very large machines, and they're characterized by being very heterogeneous. So different kinds of processors in them, and with very different performance characteristics, and also having distributed memory. So not just the usual kind of distributed memory, but very non-uniform memory with lots of differences in size and speed. And just to give an idea of the complexity of these of programming these machines, here's a little diagram that only scratches the surface. So you have a lot of CPUs, and those CPUs will have access to a large system memory, as well as registered memory that can talk to the network, and then something called zero-copy memory, which is shared with the GPUs. So if you put stuff in zero-copy memory, it can be accessed directly by the GPUs as well as the CPUs. But then, of course, the GPUs have their own several different kinds of memory that can only be accessed from within the GPU. And this is just one node, which has multiple of these GPUs attached to it, and then you have lots of nodes with a network with its own interesting properties. And so trying to actually lay out computation and data in a way that results in high performance, even for relatively simple applications, can get to be an interesting problem. All right, so the question that I ask and people like me are interested in is, how should we program these machines? Okay, so what is a good model for a programmer who doesn't really want to learn everything about all the details of these machines? They would rather focus on the physics or the chemistry or whatever their specialty is, and be able to get something out of machines like this without having to get a PhD in computer science. All right. And I have a couple of short messages I'd like you to remember from today's talk. If you don't remember anything else, this is one of them, and that's that data is what really matters. Okay, so and to drill down on that just a little bit, if you have a poor data layout for your machine, it doesn't matter how good your kernels are and how good your compute is. It's going to behave very, very, very poorly. So data is really, and data movement is your first order concern in programming these machines. And then once you've got all that right, then the kernels can matter. So how fast your algorithms are on a particular core, will make it, or a GPU will make a difference. But until the data orchestration is good, the rest of it doesn't really matter very much. Okay. All right. So what is Legion? Legion, what's come to be known as a task-based programming system. So this is different from the old synchronous model in MPI that most people are probably more familiar with. This is what's generally referred to as an asynchronous model. Task is just, we like to make up new names for things that already have a perfectly good name. So a task is just a function. But the name task indicates that this thing can be moved around the system. So a task can run anywhere in the system. It's kind of a place independent and often architecture independent. So perhaps a task can run on either a CPU or a GPU, provided sufficient back-end support for running on both kinds of processors. All right. And tasks generally operate on collection arguments. Often the tasking models have some kind of dependency graph, so you have tasks arranged in some kind of partial order in which they have to run to correctly operate on the data. All right. So there are lots of tasking models in use today. They're actually very popular. So in the cloud world, systems like Spark, Dask, TensorFlow, and PyTorch are all tasking models, so actually tasking is pretty well established. In high-performance computing, we have a different collection of tasking models. The Parsec project with George Pasilka and Jack Dungara at the University of Tennessee. StarPU is a project in France at INRIA, HPX, Hartmut Kaiser in Louisiana, and then Legion project. And the cloud versions and the HPC versions have very different characteristics, actually, and I won't get into that today, but just be aware that these are really fairly distinct application domains with different requirements. All right, since I said that data is the key, all I'm going to tell you about today is how you talk about data in Legion. I won't focus on the computing, the task aspect of it too much. I'll say a little bit, but not very much. I just want to focus on what the data model is and how you think about data in Legion, and then we'll talk about some applications. So the distinctive thing about distributed computing that's different from kind of ordinary programming is that you have to partition your data. Okay? You can't pretend that you just have one kind of uniform memory and you can put your data wherever you want, like you can when you program a single CPU system. You don't really think about where the data is placed on those systems. When you get to a distributed memory system, the programmer, or the program at least, has to be aware that the fact that the memory system is fragmented and that data needs to be partitioned and placed in different discrete memories. So how do you do that? Okay, and how do we think about that? So let me show you the Legion view of the world. All right, and this is different from. So I think this will probably be new for people who haven't looked at this kind of thing before. So let's say we want to partition a graph, just an unstructured graph, and because we're dealing with a very large machine, we're going to partition it into 3 pieces. Okay, mostly because it has to fit on one slide. Actually, is the reason we're going to partition it into 3 pieces. All right, so how would we go about that? And this is going to be for a simulation, say an electrical simulation, where this is an electrical circuit, and so charges flow along the wires, electrons flow along the wires, which are represented by the edges. So I'm only going to focus on partitioning the nodes. Okay, so we're not going to look at the edges. We're just going to look at the nodes of this graph. And the first thing we might do is actually divide the nodes into 2 sets. All right, and these sets are the sets of nodes that are going to be private to one of the pieces, so that are completely inside a piece and not connected to another piece by an edge. And then the nodes that live on the boundary of a piece. So here, all the nodes in red have an edge that connect them to another piece, and all the nodes in blue are, you know, far away from the boundaries. They are totally inside one of the pieces. Okay. So once we have kind of split our nodes into these two sets, the private set P and the shared set S, then we can talk about, you know, dividing the private set into the three the three private pieces for each of the three sections of the graph that we're interested in, and also the three shared subsets of the nodes. So just focusing on the piece in the upper left-hand corner, you know, these two nodes would be P1. These would be the private nodes of piece 1, and these 4 nodes would be the private set the shared set of piece 1, which we'll call the set S1. All right, but there is one other set that we're interested in. Okay, we don't care about just the private and the shared nodes of each piece. We also want to talk about the ghost nodes. These are the nodes that are connected to one of the shared nodes of piece 1 that are outside of piece 1, because this is where information will have to be exchanged in a typical simulation. So we'll have our pieces spread out on different processors and different memories, and then these are the pieces that share an edge where we'll have to communicate information. So, you know, the computation that deals with piece 1 has to know about its private nodes, it has to know about its shared nodes, and it has to know about its ghost nodes. All right, so we have these 3 sets, P1, S1, and G1. All right, now the interesting thing is that one piece's ghost nodes are another piece's shared nodes, right? And so really, these ghost nodes are really just another view onto the shared nodes, all right? It's a different view of the same data. And this is very common when you start thinking about how data has to be partitioned in distributed memory systems. Different algorithms, different pieces of your computation will want to view the same data in different ways. So you will have different partitionings of the same data. And that is where communication is implied, right? One task will access the data through the ghost nodes, and then another will access it through its shared nodes, and because those sets might overlap, data will have to move, information will have to be exchanged. And tasking systems can figure this all out for you just from this description of how you partition the data, because they'll know which task is accessing which subset and what the dependencies are between the tasks. Okay? All right. So in Legion, now just saying a little bit about what a program looks like, since I should show you just a little bit of code. So you have, you know, tasks are these distinguished functions that are the units of parallel execution. Regions, again, you know, making up a new name for something that's has a perfectly good name called an array. All right. Are n-dimensional tables. You know, you can think of them as tensors. They are a little bit more than arrays. They have type fields, so you can think of each element of these arrays as being an object. And then you have to declare the privileges. So this is how the task operates on its collection or region arguments. And so here we would say that this task is going to read the region of wires. That's the RW region. And it's going to read the following fields out of those. It's going to read, you know, the in pointer and out pointer, so the 2 endpoints of the edge and the current field. And then it's going to perform reductions to the private, shared, and ghost nodes for its piece, to the charge field of the private, shared, and ghost nodes of its piece. All right? And this information is used by the runtime system to figure out what tasks depend on other tasks and in what order the tasks can run. Okay? All right. And just observe that this particular task actually uses both views of the shared nodes. It actually is accessing data through the, you know, through the shared node subsets and through the ghost node subsets, right? And so, and other tasks that run in parallel will be doing the same thing, and so there will be communication that has to happen. All right. Okay, so backing up one level, the first observation I want to make is that, you know, this idea of having multiple partitions of the same data, this comes up in other fields of computer science. So this idea of having multiple views, this is actually something that the database people have done for decades. And it's something you really need for compositionality of software. So if you're somebody like me who thinks about how you build software from components, the problem is if I have two developers who both write a piece of code independently, like somebody writes a library that I want to use, my algorithm may want to view the data one way, but their library may want to view it another. And if we didn't coordinate in advance, there's no reason to assume that we had the same opinion about how the data should be viewed by our code. And so if I want to compose those things, I have to be able to support multiple views of the same data. If I want to be able to just take those two pieces of software and put them together, your programming model has to provide this. And this is one of the limitations of libraries in parallel computing today, is that they don't compose in this way. So very often, the library insists on the data being in a particular format, in a particular memory, and the application has to be torqued to adapt to that. Okay, you're forced to make extra copies or rearrange your data and write fairly complicated code just to make the library happy in this way. All right? Okay, so, and there are lots and lots of examples where this comes up. You'd like to use a visualization library, with your algorithm. You'd like to use a particular solver with your simulation. You have a data analysis pipeline that consists of multiple stages where you're pasting them together and you didn't write those stages yourself. There's a lot of examples where you want to compose things out of larger pieces. All right, so this is why partitioning is interesting. Just thinking about partitioning, like you get into fairly complicated relationships just by thinking about how you want to organize the data and what subsets of the data, which will often overlap. What subsets of the data you want to name, and those subsets, because you have multiple views of the same data, may overlap in interesting ways. So how do you actually partition the data in Legion? All right, so Legion is a little different from other systems, and it takes the view that partitioning should really be a first-class concern. And this is something that you should really have a full programming subsystem for. So Legion has a very rich subset of partition, sub-language of partitioning primitives, all of which are designed to be scalable in parallel. And you build from these primitives, you can build by composing them, complex partitioning strategies. So let's come back to our little graph example. And let's just think about how we might get this initial partition into the private and shared. Now, somebody's going to have to decide, some piece of software is going to have to decide that this is the way we want to partition the graph. And it might be something like Metis or ParMetis or something like that. So the runtime system isn't going to implement those heuristics for you. It provides more primitive building blocks for providing the names, giving a way of naming these sets. So the way we would do this is you have your region here, or array of nodes, and they have some fields. And one of those fields will be whether this is a shared node or a private node, just a Boolean flag indicating whether it's a shared node or a private node. And some other computation that's part of your program is going to fill that field in, say Metis is going to fill that in. And then we have a primitive in Legion that says, partition by field. So use this field as the flag to decide, how to partition things. And that field will be an enumerated type. It has n categories, in this case just 2. And then it will, create a shared subset and a private subset, which you can then use as you wish in your program. And the system will know which field nodes are in which set and, rearrange the data, move it around as appropriate. Okay. So partition by field is an example of what we call an independent partition. This is a partition that doesn't depend on any other partition. Okay, you just create it. Another example is to say, I just want to chop some region up into, say, 5 equal pieces, or approximately equal pieces. Okay. Now, the more interesting piece is that Legion has what we call dependent partitioning operators, and these are partitions that can be computed from existing partitions. All right, and this is what allows you to co-partition different data structures in compatible ways. So let me show you the two most important dependent partitioning operators. So let's say that this region 1 here, has a pointer field that points into region 2. Okay, so there's some connection between region 1 and region 2. And these pointers, by the way, are really just glorified indices. Okay, so they're known to be indices into region 2, but they're just like, fifth element of region 2, sixth element of region 2. All right. All right. So now let's say that region 1 has already been partitioned, and the way we think about partitioning is as colorings, because it's easy to visualize. So here we've partitioned region 1 into 3 subregions, a red subregion, a blue subregion, and a green subregion. Okay. So then to partition by image, we treat region 1 as a function from elements of region 1 to elements of region 2 using the pointer field as the function. So you can think of the arrows here as inheriting the color, and they will then taint the elements of region 2 with the same color. We just project the image of region 1's pointer field onto region 2, and that defines a partitioning of region 2. Now, because of the nature of pointers, some elements of region 2 might have more than one pointer to them. And so they will be in both subsets. Okay, so elements of region 2 might get more than one color. And you can see a couple of examples in here where an element of region 2 has, a couple, is actually in 2 subsets. And some elements of region 2 might not be part of the partition at all. So these aren't mathematical partitions. These are ways of naming subsets, of data. Okay. All right. So that's the image operation. And then the pre-image operation is just the inverse. So now region 2 has been partitioned, and it has pointers into it from region 1. And we just let the arrows, the edges, inherit the colors backwards and define a partitioning of region 1. All right, so what can you do with this? Well, so let's talk about sparse matrix representations, because I think this is something that will be familiar to many people in this audience. So let's say we have a matrix, with only some elements non-zero. The ones with letters are the ones that are the non-zero elements. Okay, so one possible partitioning here would be the compressed sparse row partitioning, where basically each row here is a subset that we want to name. We want to be able to access this matrix by rows and just the non-zero elements in each row. But another partitioning we might like to use is where we have the balanced number of elements in each subset. Okay, if we want to balance the work in some way, then we could say we just want 2 elements in each subset, and we lay them out this way. All right, so just to introduce an abstraction here to help the conversation along, we can describe this sparse matrix as a coordinate tree where we have the rows at the top of the tree, and then we have the elements of each row that are inhabited as the children, and then finally the actual values. Okay? So you can see here, like the element E there is in the first row, third element. All right? Okay, so. And these 3 vectors here are familiar sparse row representation. It's sort of typical, sparse matrix representation. You'll have 3 vectors that kind of look like this, and we can make them into 3 regions in Legion. All right, so now let's think about how we can get those 2 partitionings I had before, because just having a sparse representation and saying I want it's represented as a coordinate tree or whatever, it doesn't say how the data is divided up. Okay, so that's another step, right, in making this into a program. So if I want my row representation or row partitioning, I can take the rows, that first region, and just put each row in its own subregion, and then take an image of the elements and then an image onto the values. So 2 image operations in succession, and I will get the partitioning I want. If I wanted to balance the elements, I would start by partitioning the element region into equal sizes. That would be the independent partition. And then I would take a pre-image backwards, to the rows, and an image forwards to the elements to construct the rest of the partition. Okay, and now some of the rows. Some of the since we just, what am I saying here? Yeah, so now we will have some elements in the top there in more than one partition. All right, since their elements are now split across multiple subpartitions. All right. Okay, and so I can define those 2 natural partitionings of a sparse matrix using these images and preimages in a very compact way. So the basic point here is that you can get these different representations by deciding how to partition one piece of this representation and then using that to drive the co-partitioning of the other pieces of the representation using images and preimages. All right, so now one thing I think that's a little bit hard to appreciate sometimes is just, this is something that's not explicit in other systems. So typically when you write programs to do this, you have to write code to do all this yourself, and the runtime system doesn't know anything about what you're doing, so it can't help you. But by making this something explicit that the runtime system knows about, we can do a lot of optimizations, we can do a lot of automation of parts of the programming process that users don't have to do. And it makes it much easier to switch your representation. If you didn't like the way you partition the sparse matrix, changing it now is just changing a couple lines of code instead of recoding large parts of your program. Okay? So we've used these kinds of techniques to build flexible libraries that are now parameterized over the partitioning strategy. Okay? Because we have a programmatic representation of the partitioning, we can make our programs more polymorphic in how things are partitioned and delay that decision until you're actually using the program and then pick, do I want to balance the elements per region in the sparse matrix, or do I want to work on a row representation of the sparse matrix? Okay, it's just a question of how you change the partitioning. So let me tell you about a few libraries. So distal and sparse distal, SP distal, are really DSLs for tensor algebra in Legion. And you can think of this as you write your tensor algebra expression, and then Legion, and then distal and SP distal will generate a Legion library for that particular tensor algebra expression. Okay? So for example, if you want distributed matrix multiply, that is one tensor algebra expression. But you can write any tensor algebra expression you want, including non-standard ones, and get custom code out for that can be plugged in as a library in a Legion application. Okay. So speaking of matrix multiply, because it's a DSL and it's easy to write these things, we've written all the traditional GEM algorithms, distributed matrix multiply algorithms in this DSL. This consists of describing the target machine, because often these algorithms want to organize the machine in a particular way. The middle column is how things are distributed and partitioned. And then we also have to talk about the kernels themselves, okay, and how they interact with the partition. And there's a scheduling language for that. It talks about in what order things should be iterated over and things like that. And then plotting, here is Cannon's algorithm versus things like Scalapack and Cosma. Cosma is the current world leading algorithm, and this is the handwritten implementation of Cosma, and comparing our automatically generated version of Cannon's algorithm to that. And so the Cannon's algorithm is automatically generated by our DSL, maybe just a few lines of code, gets within 95% of the handwritten Cosma implementation, and it's faster than, more scalable than Scalapack. So just to give you an idea where it sits in this world. So not quite as good as absolutely handwritten code, but better than the most popular libraries that people use. And then the GPU version, it gets to about 85% of Cosma. And this sawtooth behavior, that's a property of Cannon's algorithm, which is exactly the thing that, so at different node sizes, depending on how many nodes you have, you get performance that goes up and down, and that's exactly the thing that Cosma fixes. But then the nice thing about this tensor algebra DSL is that you can write other odd tensor algebra expressions that don't have the investment that matrix multiply has had, and get good performance. So here's just a bunch of various tensor algebra expressions pulled from the literature and run through our DSL, and then you can see that the gap to other systems that support general tensor algebra is much bigger here. And some GPU numbers as well. Those were CPU numbers on the previous slide. Here's comparisons running on GPUs. And then I also mentioned that we can handle sparse tensor algebra, and the key there is really the partitioning stuff I showed you in the previous slides. Here there are confidence intervals, because with sparse computations, depending on the sparsity pattern of the example you use, the performance may vary a lot. And so these are algorithms that were run on a bunch of different sparse matrices, and we're showing the spread of performance for those matrices. And the blue bands you can see at the top are SP distal. And so generally, this is doing better than PETC and Trilinos by at least a little bit on standard benchmarks like sparse matrix vector multiply. And then on things that are non-standard, where we can generate custom code that that other people don't focus so much on optimizing, the gap is larger. All right. So just talk about some other libraries where we've exploited this ability to kind of automate partitioning and to have an expressive programmatic way of doing partitioning. So in FlexFlow, it's a Legion library for DNNs. It's kind of a drop-in replacement for TensorFlow or PyTorch. And the basic idea is to exploit Legion's data partitioning to partition the data in ways that TensorFlow and PyTorch don't know about. So if you don't know much about TensorFlow and PyTorch, they can parallelize applications, deep networks in certain ways. But there are lots of other ways you could do it that they don't express. And Legion's partitioning mechanisms are expressive enough that we can capture those patterns. All right, so you might think, okay, maybe there's an opportunity to do better, by exploiting a partitioning method that PyTorch and TensorFlow don't know about. And that turns out to be true. But that's actually a lot of work. And so then the second idea is we'll just automate that search for the better partitioning strategy. So have some way of searching over lots of partitioning strategies and then pick the best one. So auto-tuning the partitioning strategy. Okay. And just as an example, I think this is the inception network. So here's what data parallelism looks like. And here we just have two dimensions, the sample dimension, which is the standard data parallel dimension, and then parameter dimension. So there's something called parameter parallelism in deep networks, and you can do partitioning in that dimension. All right, so TensorFlow and PyTorch only know about sample partitioning, and so every layer of the network will be partitioned the same way if you're running on 4 GPUs, and you get something that looks like that. But if you search using FlexFlow, it's going to pick something much more complicated, where sometimes for some layers it's partitioning in the parameter dimension, sometimes it's partitioning in the sample dimension, and sometimes it's partitioning in both. For some networks, you actually want to do multi-dimensional partitioning. Okay? And the result of this is, in the latest version of this, which we call Unity, because it combines a couple of different ideas, you can see that we're competitive with hand-tuned models. Like BERT Large, which have had a lot of handwritten investment to parallelize those models, and this generalizes to lots of other models, including models where people don't spend all the time doing the optimizations by hand, and there you start to see a really big gap, like the Candle model, which is a DOE project. All right, so. Let me mention two more libraries. Okay, so I said there were actually two things I wanted you to remember from this talk if you didn't remember anything else. One was how you lay out your data, how you partition your data, that really matters, okay? More than your compute, like that's your first order concern. The second thing is that actually there's now a library called QNumeric, which as of this week is in beta, so it's actually now kind of a supported product from NVIDIA that does all the partitioning for you if you write a NumPy program. So if you write in NumPy and you use QNumeric, then you can take your unmodified NumPy program and run it on a supercomputer. And it'll figure out how to chop up the NumPy arrays and then map it down to Legion. Okay. And so it essentially takes this same idea of, well, once we have a programmatic way of partitioning, we can automate that partitioning. And they've done all the engineering work to do this for all the NumPy operators. And so here's an example of a CFD solver. It's a 2D solver from a class. I mean, like this is like the final project. But it's a fairly complicated thing. And they took it somebody else's program. They took it unmodified and scaled it up to 2,000 GPUs. Okay, so. And then I'll mention one more project, one more library. This is very recent work, actually. This is hot off the presses. So, Q-numeric kind of handles the dense case, but there's a lot of sparse things you'd like to do that are coded up in SciPy in Python. So one of the things we've done very recently is to take that work on sparse tensor algebra and kind of port it over to support parallel distributed SciPy and combine it with Q-numeric. Okay, so that you can do sparse computations as well at the Python level and have all the partitioning and everything be automated. All right. And so here, for example, is a CG solver in what's called Legate Sparse. And you can see it's pretty competitive with PET-C at the top. Not quite as good as PET-C, and we wouldn't expect to beat the hand-engineered system, but a lot more performant than SciPy, which is the numbers down here at the bottom. Okay. And then here's a geometric multi-grid solver. So this is kind of thing that's sort of a little bit complicated to write and to get correct. But this is only 300 lines of Python. And again, you get pretty good performance. I don't want to claim you always get great performance because automated heuristics aren't going to always do as well as people. And so you can see that the numbers tail off. But if you compare it to what you get today, which is like single GPU performance, I mean, like all of a sudden you can run on 64 GPUs and get pretty good performance. And this is just out of the box with this. Okay, and this is a research project, I should say. This is not yet integrated into any product, but this is coming at some point. All right, so to summarize, in distributed computing, data partitioning is key. And expressive data partitioning, in Legion at least, that we have this idea of independent partitions and then building more complex partitions through these dependent partitioning operators that compute new partitions from old partitions. And this enables these flexible libraries that can adapt to clients, things like SP-distal, and the automation of the partitioning, libraries like FlexFlow and Q-numeric. And with that, I don't want to go into our break, so I will stop and we can take some questions if there's time.
Any questions? Venkat?
Alex, great talk. I've been watching Legion for about a decade now, so it's something I've looked at for a while.
Very patient.
So my question is, you said data is important, no disagreement, but not all data is equally important. And how do you determine what is important ahead of time in this parallelism?
Right, and that's a great question, and another perspective on what we try to do in this project, and this is really a lesson we've learned over time. It's not something we knew at the beginning. There are many decisions like that. Yeah, so data partitioning is your number one thing, but a lot of the data, there's always a kind of 90-10 rule. I mean, there's some things that matter a lot, and there's some things, a lot of stuff that doesn't matter at all. And the problem is exactly that it's very hard to predict up front what's going to be important, okay? And usually you're better off getting the thing working. And then once you have feedback, like we can actually measure things, then you can make these decisions. And so what you really want is a programming system that gives you late binding. You want to be able to get things running and then have it be easy to change these decisions, on the back end. And this, I think, is the real problem with the way, I had trouble for years articulating why I didn't like MPI programming. But I think this is the problem with the kind of traditional way of writing bulk synchronous codes, is that you wire in all these decisions in a way that's very hard to change. So if you make a mistake, this isn't so true today, but like 5 years ago, if you wrote a bunch of GPU code thinking that was super important, and then it turned out that was actually a mistake because you were using all your GPU memory, and that was not a very important kernel, and that really should run on the CPU, you had to rewrite the whole thing, right? For the CPU and rearrange all your communication. You had to basically, turn the program inside out to make that one change. So we're moving towards systems like Legion where you can actually make these decisions, at the end. And they're really like one-line decision. Oh, I want to move this from the CPU to the GPU, or vice versa. Oh, I want to put that data in a different memory. Okay, these are things you can tune after you have the program running without huge effort. Yeah.
Okay, so
Conceptually, how does like QNumeric compare to like QPy? Is it conceptually the same idea, or is it just a better implementation, or?
Yeah, so the difference is, so QNumeric is a drop-in replacement for NumPy. I mean, it is designed that literally you take your NumPy program and you change the import line, and that's the only change you make. Under the hood, there's a completely different computational model.
Okay.
Like the standard computational model in QNumeric is that you're running on CPUs, and maybe it's multi-threaded, right? So it knows about one multi-core chip, essentially. QNumeric has a model of a distributed machine with accelerators and the ability to say, to talk about partitioning the data and partitioning the compute to spread it out over that. So, just a completely different implementation. The SciPy story is similar. Like the SciPy work we've done is like literally, I mean, the constraint is it should be literally the same program, but then under the hood, it maps down to this task-based framework.
Okay.
Yeah, so this was really impressive. Kind of following up on Venkat's question, but also slightly different. So you said, you start the program and then you make some decisions, right? But to a great degree, based on how data is moving, that can also be automated, right? So those kind of things also don't need to be done by the user. So that's the first question. And then the second thing is, if something in the problem changes, like adaptively, in situ, is there some future ideas where?
Right. Yeah, so I'll turn that into three questions. Okay, so first of all, the model of tuning your program that I suggested was, once you have the program working, you would run it and gather data and then make decisions about, where things are placed, how data is partitioned. You'd be able to change these things. Okay, and that is the way it is today. And then we have some libraries that automate pieces of that. At a lower level, like if you just think about a program running, with fixed settings, in Legion, as you said, the data movement is automated. So based on where the system decides to place the tasks, like if a task is run on this GPU on this node and another task is run on a GPU on another node, and they use the same data, the system will figure out, the output of this task has to be moved to the input of that task, and that is all automated and transparent. Okay, and we spend a lot of effort to optimize that. Yeah. What was the other question? The other part of the question?
So I had a question on in situ.
Oh, yeah. And so then for more dynamic applications, where things will be changing online. So we haven't explored this as much. Okay, so this is an area where we just haven't, invested as much time. But Legion all these decisions in Legion are made dynamically, so we're set up for that. And this is a lesson we learned a long time ago that, you need to make these decisions dynamically and be able to support that, or you will have trouble when you get to applications where the characteristics change over time. Yeah, and we do have some examples like load balancing and things, but I wouldn't say we've done a lot on that yet.
Okay, let's thank our speaker again.